Good morning. I'm going to talk about permutation tests for MVPA, but not only for MVPA, because the principles are very similar. Okay. Why would you want to use a permutation test? Pradeep just mentioned it. It's not enough if you compare classification accuracies that have been cross-validated, because you might find a difference between classification accuracies that is not statistically significant. If you're interested in statistical significance, you need a significance test, and most parametric tests are not useful for that because distributions are not known, especially the distribution of some statistics in MVPA, like classification accuracy or IUC, are not known. A nice thing about permutation tests is that they make weaker assumptions about not only the distribution of the test statistic, but also about the distribution of the data that you put into the classification or other multivariate analysis. They don't have no assumptions, so it's not completely non-parametric. You still have to be aware that that you can actually make the assumptions of a permutation test. This is one of the things I'm going to talk about. Permutation tests, if they are applicable, provide exact inference. So you have a guarantee that the error rate that you design the test for is actually the error rate that you're getting out of the test. And it is a very general scheme. It rests on general principles that can be applied in many different circumstances. And especially it can often be applied in exactly the same way in uni and in multivariate analysis of the same data. In this talk, I'm going to give a few test descriptions, but the main point is not recipes, but to explain the basic principles underlying permutation tests, especially the principle of exchangeability. Simple example, univariate example. Let's say we have two different samples, 3 different numbers in each sample. So we have sample A, 714, sample B, 639. And we're interested in whether there is a difference in the mean in the underlying distribution, so the source from which these numbers A and B have been taken from. In order to do so, we compute a test statistic. In the simplest case, the mean of the samples. Mean of sample A is 4, mean of sample B is 6. Then we compute the difference of the two, x bar B minus x bar A equals 2, so our test statistic is 2. If there is no mean difference between the two distributions, or more specifically, if there is no difference between the distributions sample A and sample B have been taken from, then we can exchange samples between the two values between the two samples. So if we have the original data, for example, we can exchange 7 and 6, or we can exchange 1 and 9. Then we get permuted data, and to the permuted data we apply exactly the same computation, difference of means. In this case, we have a value of minus 2.67. And this we do optimally, if it's possible, if it's feasible computationally, for all possible permutations. In this case, it's possible. If we have 3 values and 2 samples, they're all independent, we can all exchange them. Then we have 20 permutations in total. So here in this list, all the different permutations have been enumerated from number 1, which is the neutral permutation, the permutation that doesn't change anything. So in this case, we have the original data, until permutation number 20. You can see the values of the permutations of the permuted data in the second column, the value of the test statistic in the third column. Now what we do is we sort these permutation values, including the original value, which was 2, so we can compute the rank that corresponds to each of the permutation values. The highest rank is associated with the highest value, 4.67 in this case. The lowest rank, 20, with a value minus 4.67. In such a situation where we have a symmetric situation and we have a symmetric test statistic, it's often the case that the permutation distribution is also symmetric. In particular, the original data, the unpermuted data, also get associated with a rank. So value 2 has a rank number 5 in the total set of 20 values. Now, if you simply want to do a test at the standard significance level of 0.05, because we have 20 permutations, we could only say that there is a significant difference between the two samples if the ranking of the actual data would be 1. In this case, we have 5, so it's not significant. Or we can also divide the rank of the original data in the distribution of the permuted values divided by the number of permutations, 5 over 20. This gives us a p-value which we can as well compare, for example, to a significance level of 5% and to decide whether it's significant or to some other significance level. So this is a basic procedure of a permutation test. With the same way, we can also test for a decrease in the mean. The first test was for an increase of the mean. Is the mean of B larger than the mean of A? In order to check for a decrease in mean, we simply use the test statistics x bar A minus x bar B. In this case, we get a p-value of 0.8, again not significant. Or we can do a two-sided test, see whether there's any mean difference at all. In this case, the test statistic would be the absolute value of the difference of the means. Now the p-value is 0.5, so again not significant. Something important to notice here is that because we take the modulus, the absolute value of the permutation values, each permutation, and we had a symmetric permutation value distribution before, now we have every permutation value double, so we have 2 times the value 2 times the value 4.67, and so on. Because before it was 4.67 and minus 4.67, or 2 and minus 2. In such a case, we have to pick the rank conservatively. So instead of giving the original value to the rank 9, we give it the rank 10 in order to get a p-value which, if then compared to an alpha level, to an error level, will give a valid significance test. This is the general procedure for a permutation test. Before we had an example. So what we have are data. We have a test statistic. We can basically choose this test statistic any way we want. So it can be something multivariate, something univariate, can have very complicated computations in there. We choose a significance level, alpha, so kind of the error probability that we are prepared to accept. And we need the possible exchanges. And the important thing is this, from a permutation test point of view, is this possible exchanges. What exchanges can we actually apply to the data in order to conform with the null hypothesis? I will talk more about this later. But if we have these things, we first compute the test statistic for the original data, call it T1, because 1 is a neutral permutation, so it's based on the original data. Then we compute the test statistic for all permutations, Ti for I equals 2 to NP, where NP is the number of permutations that are possible. It is also possible in this case to use a random selection if there are too many permutations to actually compute it for all the values. And here we can just take a random subselection of those permutations 2 to NP. What we have to take keeps the original, the neutral permutation 1 in there. Then we compute the rank of T1, which can be simply done by looking at all the values in the permutation distribution which are larger or equal to T1 and count this number. This can be expressed in with this bracket, so-called Iverson bracket, sum over I equals to NP of brackets Ti larger than or equal to T1, where the brackets mean if the condition in the brackets is true, it has a value 1, and if the condition is false, it has a value 0. Now we have the rank R. We determine the p-value by dividing this rank by the number of permutations. P equals R over NP. And then we can make the test. If P is smaller than or equal our predefined alpha level or error level, then we can reject the null hypothesis. Importantly, in this, if you use this way to compute the rank, the sum formula with these brackets, then you can always already be sure that you have computed your rank in the appropriate conservative way in the case of ties. The permutation test is exact if your chosen alpha level is an integer multiple of 1 over NP, the inverse of your number of permutations, and if there are no ties. Otherwise, the permutation test will be conservative. So you will have a lower error rejection rate than you designed the test for. Chris, should we try allowing questions in between for interactivity? Should we just test it?
Oh yeah, we can try. So
okay.
Hold on, I need to.
No, not the quiz questions, just general questions from the audience.
Oh yes, if you want to.
So I thought it should be, there was this idea to make the lectures more interactive, so I thought maybe it's a good idea to allow questions in between. If you have any questions up to now, please stand up and say so. Yeah? Theoretically, if you have less assumptions, you could achieve a lower power. In those applications where I looked at it, power is basically limited by the number of permutations you can do. So, for example, if you have a situation in which you can apply a t-test and you apply a permutation test instead, most of the time I find very similar p-values, so I don't find a big difference between them. But theoretically, it is possible, yes. Any other questions? Oh. No? Okay. Okay, now for exchangeability, the principle underlying permutation test. What does exchangeability mean? The simplest case of exchangeability is you have if all your samples are independent. They are independent values drawn from a population, and this population is the same. So this is the classic IID, independent identically distributed case. Here in this picture, there is a joint density of two samples drawn under this condition, IID. Samples are not normally distributed, but in this case, they are t-distributed, I think with 3 degrees of freedom. And you can see that it doesn't have this nice spherical normal appearance, but it has heavier tails. But still, in this case, we have exchangeability. Why do we have exchangeability? The idea is you look at this joint distribution of these two values that you have drawn, x1 and x2. The color in this plot describes the joint probability density, so the probability to find the specific combination of values. And the condition of exchangeability is given if you can swap x1 and x2, which in this case, in this visualization, simply means that you swap the plot around the main diagonal. You make a mirror symmetry, a mirror swap around the 45-degree angle, and the joint distribution remains unchanged. This is exactly what exchangeability means. If you exchange things, the joint distribution will be invariant. It will have the same values. Now, if in this case, again, we're looking for a mean difference, and now the two distributions have the same shape and width, but the means of the two distributions are different. So x1 is from a distribution with a mean of 0, x2 is from a distribution with a mean which is larger than 0. You apply the same mirroring operation, then you get a different joint distribution. So in this case, there is no exchangeability. The important thing to notice is that exchangeability refers to your null hypothesis. Or more specifically, you want exchangeability under the null hypothesis, but you do not want exchangeability under the alternative hypothesis if the null hypothesis is not true, because then this permutation scheme allows you to distinguish between the null situation and the alternative situation. Data can also be exchangeable in this simple two bivariate case if they are dependent. But this dependency is symmetric. So in this case, there's a certain correlation induced between these two variables. In some marginalization, they're still t-distributed. So again, it's not simply normally distributed with a certain correlation, but of course it would also work. And then in the first case, again, both distributions have the same shape, the same mean, and they have a symmetric dependency structure. And if then you switch x1 and x2 through, you do this flipping over the main diagonal, you see that the joint distribution stays the same. So you have exchangeability. But if one of them has a higher mean, then if you do the swapping of x1 and x2, you get a different joint distribution, so you have no exchangeability. So again, in this case, which is not normal, the symmetry is not a simple correlation, the dependency is not a simple correlation, but the dependency between x1 and x2 is symmetric. You can again use permutation to distinguish the null situation. Mean is the same from the not null or the alternative situation. Means are different. Something you have to be aware of, though, is that sometimes exchangeability is violated, or the null hypothesis may be wrong, in a way that you're not intending. So let's say you want to make a test for the mean, And you assume exchangeability. Exchangeability implies that the mean is the same in both samples. It's simply the same. So the distribution is unchanged under the exchange. But in this case, you have a second situation shown in the lower two panels, where indeed the mean is still 0 in both in x1 and in x2, but the variance is higher in x2 than in x1. So if in this case you flip over, you get now a distribution where x1 has a higher variance than x2, which means exchangeability is violated. So exchangeability is a very general condition. It can applied in many conditions where parametric tests can't. But it's not that it's like a panacea, that in every possible situation you're just interested in the mean difference. You want to know whether the mean difference is 0 or not. You just apply it. No, sometimes it won't work because, for example, the variance in one sample is larger than in the other sample. So you still have to think about your distributions, and you still have to make sure that the assumptions of exchangeability for distinguishing between the null hypothesis that you're interested in and the specific alternative that you're interested in are reasonable, are well-founded. Okay, let's try it again. Any questions so far? Okay, thanks. Let's go on. Now for some concrete examples of tests, univariate and multivariate test examples. The first I already showed before, now in a little bit more detail. This is, you have two different samples with values which are also independent. And they are sampled from two univariate distributions. And you have the null hypothesis that these two samples come from the same distribution, but you don't want to say anything more about it. So it doesn't have to, for example, to be normally distributed. Under this assumption that they are independent and come from the same distribution, the IID situation I described before, then you can exchange values between the two samples. All of these blue arrows indicate possible exchanges of values between the two samples. There are more exchanges within samples, but in the end, your test statistic will only depend on which values are in the one sample or in the other sample, so these exchanges are not so important. So you have plenty of possible exchanges. What you do is you compute a test statistic, in this case, a difference of sample means, x bar b minus x bar a, and what you get is a permutation version of a two-sample t-test. In case you use a test statistic like this one, which is sensitive to the difference of means. Okay, now the multivariate case, which is completely analogous. Now you have multivariate samples, multivariate values, which is now indicated by these caches with several elements in them. These values come under the null hypothesis from the same multivariate distribution. They are independent, so we can still apply the same exchanges. But what's important to notice here is that the exchanges now apply to the multivariate values. So you always exchange vector values between samples. You never exchange single parts of these vectors between samples, unless you have a different null hypothesis. But this would be the standard situation. For example, you want to know whether there's a multivariate difference between two distributions. The null hypothesis that there is none. From the way you obtain your data, you have reason to assume that the samples are independent. Now for example, what you can do is train and test a classifier in a cross-validated way. Okay, there are a few samples here, but let's say the first two columns are put into use for the training of the classifier, the last one for the testing of the classifier, then vice versa in a cross-validated way. You have an accuracy, and you can do exactly the same as before. You compute the accuracy for the original data. You compute it for all of the different permutations. Again, because we have 3 values and 2 samples and all exchanges are possible, we have 20 different permutations. So if your actual accuracy is the largest accuracy in the distribution of these 20 different values, you can say there is a significant difference, a significant multivariate difference between these 2 samples. A problem that can occur here, I mentioned before that in a permutation test, if you have ties, if you have several times the same value, you have to go the conservative way. Or there's also an alternative where you can randomize, but it doesn't really have much advantages. If you have accuracies and few data points, you will often have ties because there are only a few possible values of a classification accuracy. So in this case, it might be better to use another multivariate test statistic like AUC or something that is based on a multivariate model. But the test itself will remain valid. It will just have a very low power because you have all these ties, which makes the test conservative. One application example for this kind of two-sample multivariate permutation test would be the classification of subject-specific patterns. Maybe patient data, patients, you have two different groups of patients, one a control group, the other one a treated group, or how do you say, a disease population, a non-disease population. You look at patterns in structural fMRI. You put them into a classifier. This kind of test you could apply in this case because you can reasonably assume that data from different subjects is statistically independent. Now, dependency. Something that we also very often have is that we have a very specific dependency structure in the data, which is in classical statistics called paired or repeated measures. So let's say you have, again, two samples with three different values, but the first value in the first sample and the first value in the second sample cannot be assumed to be statistically independent. For example, because they have been obtained from the same subject under different experimental conditions. So in this case, we have a restricted exchangeability structure. We have to make exchanges so that this dependency structure stays the same under the exchanges. And because we have this pairwise dependency structure, we also can only do pairwise exchanges. So we can only exchange value 1 from sample A with value 1 from sample B, or values 2 from sample A with value 2 from sample B, etc. Which also means that we have less permutations, therefore it's, depending on the number of samples, it's harder to get lower p-values. But still the same procedure applies. You compute, in the univariate case, you compute the difference of sample means. In this case, this would be the analog to the paired t-test. Or again, in the multivariate case, our values are multivariate values, they are vector values, but again, we have this dependency structure. We can only exchange within these dependent pairs under the assumption that the dependency is symmetric. And again, we can do something multivariate like train and test a classifier, obtain a classification accuracy. One example for that, as I mentioned, would be classification of condition-specific patterns across subjects. For example, you have run-wise beta patterns estimated from a GLM. You have one pair of such patterns from each subject, so you have dependency between these patterns within subject, but not between subjects because you can assume that the subjects are independent. Another example would be if you have a multi-session fMRI data set and you obtain patterns, multiple patterns within subject, you can reasonably assume that the different sessions, if the pause between them is long enough, are independent. But you cannot assume that patterns estimated from the same session are independent, so you can only exchange patterns within session or within run. Okay. I'm still asking, even though nobody wants to. Any questions at this point? Okay, let's go on. Now I'm going to talk about a specific situation where exchangeability is limited. One classic example in our field in imaging is fMRI time series. I think Pradeep already mentioned that. fMRI has serial correlations in the errors, so the randomness of estimates from a single trial is correlated with the randomness in the next trial or in the next volume, depending on how you look at the data on a trial basis or in a volume or a scan basis. This is indicated here by this sequence of circles with connections in between. You have not that much dependency, for example, to the second to next trial, but to the next trial, very often you will have dependency. Now let's say you have these different trials belong to different experimental conditions A and B, and you want to apply a permutation test. Now you have a problem, because, for example, you would like to exchange the labels, exchange the values between these middle trials belonging to B and A. And as you can see, the dependency structure is completely different. There would be other ways to visualize this, but I think this is strong enough. You have data with a completely different structure. So on first look, there is no exchangeability in fMRI time series unless you have really widely spaced trials or you do some other checks. Chris, I see the countdown running out.
Yeah, just go on.
Okay. We still have time though, right?
Yeah, the coffee break is at 10:15.
Okay.
So we just do the quiz as well. So
Okay.
if you could leave 5-10 minutes.
Good. Okay. That means we have no exchangeability of values of subsequent values in fMRI time series. Now there's a different approach to this, which is not a permutation test. It's called a randomization test. And in this case, the idea is that, okay, your data are dependent, but maybe your trial sequence, the way you allocate conditions to trials A and B, has been randomized. And this randomization is independent. So there is no change in probability for the second trial to be A or B if the first trial has been already A and B. So you could say, because the trial sequence has been randomized, I can now apply exchanges not to the data, which are serially correlated, but I can apply them to the labels associated with the data, because they have been randomly, independently assigned. The answer to this idea is yes, it is possible. It does not lead to a permutation test, because a permutation test is based on exchanges based on the structure of the data itself, the distribution of the data itself. This kind of test is called a randomization test. There's a huge literature about these kinds of tests. However, there's also a drawback, because we do not rely on the distribution of the data, but we rely on the distribution of the labels. What we get is a test that is exact if we apply the right exchanges with respect to the distribution of possible labels. So the experiment we have done with specific trial labels, with specific experimental conditions, and then we relate this to the set of other possible experiments we could have done and assume that the data are the same. This is different from a permutation test, where we assume that the labels are given. We have just done this experiment, and we think about what other data could have been obtained under this assumption of exchangeability. So if you're in a really tricky spot and you need this kind of thing, look at the randomization test, but please be aware that you do not get the same guarantees from a randomization test as you get from a permutation test. For this reason, it might be easier to not look at trial-wise values to exchange, but, for example, to run-wise means in fMRI or to GLM parameter estimates, because then again you can make the argument that, okay, there's a dependency structure between these run-wise GLM parameter estimates, but the dependency structure is symmetric, so you can again have exchangeability. Another approach would be to widen the time series, which is a standard approach in parametric testing in fMRI. So you could have an estimate of the strength of the serial correlations in the time series, and then you use this estimate in order to remove this autocorrelation. First of all, then it's not really a pure permutation test anymore, because you use some model-based, some parametric estimation of the autocorrelation structure. But even if we ignore that, it's not a general solution, because exchangeability is also limited. There's a second problem by covariance. So look at this design matrix on the very left. Vertical axis is time or measurements. Horizontal axis are the different regresses, your idea of how the data will look like, what kinds of effects there could be. We have we have one trial in each of these three different conditions in the first three columns with a shape roughly that of nature F. And then we have some covariate which might come from a motion regressor or something else like that. Now, under the null hypothesis, in this case that the effect of condition 1 and condition 2 are the same, you can remove the difference between them. That's a plot in the middle. And you get a reduced design matrix. So your assumption, your model assumption for this null hypothesis is that your data are described by these three regressors, where the first one is simply the sum of the first and second from the first. So you have now no difference between the first trial and the third trial, even though they belong to conditions 1 and 2. So you could say I could exchange the third scan and the, okay, sorry, I don't have the numbers, the corresponding later scan as indicated by the arrows, because now there's no difference between condition 1 and condition 2, so these scans should be identical. The answer is no, not really, because you have other regressors. You could have an effect of the third condition, or you could have an effect of the covariate, and in this case, you cannot assume that these two measurements are exchangeable. You have to, again, do something to deal with the covariates. Okay, since we're running out of time, apparently, just quickly a few other things. Multiple comparisons, especially in fMRI. We often do tests not in a single location, in a single voxel, but in many voxels. In this case, we often want to control not for the voxel-wise or the single error of rejection of null hypothesis, but we want to correct it to get control of the family-wise error. The precise correction depends on the dependency between the different tests that we're making. We're making one test in voxel 1 and voxel 2. There's spatial correlation between them. If we just say these are two independent tests, we are correcting too strongly. And nicely, permutation tests provide a way to correct precisely for this correlation. And the idea is to use the same permutation across tests. So basically, we have a two-dimensional scheme. We have many different tests, we have many different permutations. We apply the same permutation across all tests, the second permutation across all tests, and then we can test whether there is an effect somewhere using the maximum statistic. What we do is we compute the statistic, the maximum of all the test statistics in the different tests across separately for the different permutations. And then we can use this maximum statistic in the same way to compute a p-value for the null hypothesis that there is no effect anywhere. And we can also use this distribution of the maximum statistic in order to compute a corrected p-value at every single location by now comparing the original value of the test statistic not with the permutation values of itself, but with the permutation values of the maximum statistic. And the second thing I would like to mention is we can go beyond permutations. Permutation tests are the standard way this kind of test is done. But there's a more general principle underlying permutation tests, and the idea here is that we have to find a group of transformations of the data. And under this group of transformations, the joint distribution of the data, if the null hypothesis is true, is invariant. In our case, it were just exchanges, so flipping around axes, but we could have different transformations. And then we do the same thing. We use all of the transformations, we compute test statistics compared to the distribution of test statistics. So a permutation is just one case of a transformation, and this principle of exchangeability that I talked about before is just one case of the general principle that we have invariance of the joint distribution under transformations. And I should mention that this term group, as in group of transformations, has a specific mathematical meaning. It means if you have two different transformations in your group, you combine them. So you first apply the one, then you apply the second. You get a combined transformation. This transformation has also to be in the set. These are the two conditions under which the general transformation test is correct. There's one example of that which is often applied, which is based on mirror symmetry. In this case, we don't exchange two different values, but we exchange a value with its negative. And the assumptions underlying this is that the distribution is mirror symmetric. So we replace x by minus x. We have a symmetric distribution. Symmetric are around 0, so the mean is 0. We flip left and right. We get the same distribution invariance of the distribution under this transformation of mirror symmetry. If the mean is different, so okay, the distribution is still mirror symmetric, but not around 0, but around some other mean value. We apply the same flip, we get a different distribution, no exchangeability. So flipping signs, exchanging a value with its negative, allows it also to test the null hypothesis of mirror symmetry around mean value 0. And there's another example which might become important in the future, so-called rotation tests. And in this case, our joint distribution has to be spherical, which means it's invariant under rotations. We don't flip the different axes anymore, but we apply an orthogonal transform or rotation in the space as indicated by this curved arrow. And you see if the distribution is spherical around 0, you apply this rotation, you get the same joint distribution, you can do this. If the distribution is spherical but around a non-zero mean value, you apply the rotation, you get a different joint distribution. So you have no, well, in this case, not exchangeability, but transformation invariance. So you can use rotations in order to test the null hypothesis of spherical distribution around a value, a mean value of 0. Okay, there's some further reading, and I'll leave it at that.